Good evening all. Today let us discuss about the combinational logic circuits. So combinational logic circuits. So combinational logic circuit is a digital system in which we provide an input and take the output. It can be any application, like it can be a adder circuit, or it can be a subtractor circuit, or it can be a multiplexer, whatever it is. Combinational logic circuit is that, which is a design circuit which provides the required output only based upon the input that is given at that state. So it doesn't have a memory unit and it doesn't have a feedback. So that is a major difference between a combinational logic circuit and a sequential logic circuit, where the sequential logic circuit will be having an input, will be providing an output, and based upon the previous output, the input will be altered. So we have a feedback. So now let us discuss about the combinational logic circuits. So combinational logic circuit is the design of a logic digital system for any of the application. It can be a design of an adder, or it can be a design of a subtractor, or it can be a design of any application. So first of all, let us see what is the systematic procedure that is required for designing a combinational logic circuit. First thing is that understanding the problem statement. Understanding the problem statement. So first of all, we should understand what is the problem statement for which we need to design a circuit. So what is the purpose of the application? Why? Because unless we have a clear idea about the problem statement, it may not be possible for us to assign the number of possible combinations or the number of possible cases that we need to take into account in order to design a digital circuit. So understanding of problem statement is a very first step. Then based upon that, we can take into consideration the number of input variables and the number of output variables required. Then based upon this number of input variables, we need to analyze the possible combinations, analyze all the possible combinations of the input variables and need to check the possible outcome, possible output, and to check the possible output, and to check the possible output. Then formation of the truth table for the same. Formation of the truth table. Then obtaining the Boolean equation, Boolean expression to design the logic circuit. To design the logic circuit. Then once after getting the Boolean expression, we can reduce or we can optimize the logic circuit by using various Boolean laws. So finally is the logic circuit design. So finally it is the logic circuit design. So now let me just give you the idea. So very first thing is that, first of all, we need to know what is the actual problem statement. And second thing is that what are all the number of input variables that are involved and number of output variables that are required. So analyze all the possible combinations of the input variables and to check the possible output which has to be obtained for all the possible combinations of the input. Then for this input variable and output variables, we need to frame a truth table. And based upon that, we need to get the Boolean expression, which will be helpful for us in designing the logic circuit. So this is the systematic procedure which we need to follow in case of the combinational logic circuits. So now let us discuss about the adder circuits. So from the term adder, it might be very clear to you that we are going to perform the binary addition. Okay. So we are going to discuss about the adder circuits. So it means that our ultimate aim is to proceed with binary addition. So when you go for binary addition, before that, let us make sure about the rules of binary addition. So coming to rules of binary addition, so say for example, if you are going to take input A and B, so when you are going to take 0 plus 0, obviously the output is going to be sum and carry. So these are the possible input variables and these are the possible output variables. So when we add 0 plus 0 in binary addition, we get the value of sum as 0 and there is no carry. Then what is the next combination? A can be 0 and B can be 1. When you add this, the sum is going to be 1 and we are not going to get any carry. And what will be the next combination? 1 plus 0. So obviously the sum is going to be 1 and the carry is 0. So when both input A and input B are 1, then your sum is 0 and your carry is 1. It is because 1 plus 1 in binary addition, we get 1, 0. And this is the least significant bit where this is actually accommodated under sum and this is accommodated under carry. So here, if you just look at, sum will be 0 and carry will be 1. So these are the rules of binary addition. So when you go for A value as 1, B value as 1, and one more 1 if added, then obviously 1 plus 1 is 1, 0. When one more 1 is added, the output is going to be 1, 1. In which case, the sum is 1 and carry is also 1. So the sum and carry is 1 when we are going to go for 3 ones. So now we are going to observe the binary addition of 2 bits, which is so called as half adder, and followed by binary addition of 3 bits, which is so called as full adder. So I hope I have given you a clear explanation about the combinational logic circuit and the systematic procedure that has to be followed for designing the logic circuit, whatever might be the application that has been given. So now let us move on to half adder. So coming to half adder. So half adder is the digital design which will be helpful for us to add a 2-bit, to make an addition of 2-bit binary. So now let us take the input. So we know very clearly it is binary addition. So binary addition of 2 bits. So input variables are A, B. So if you have 2 input variables, possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And what is going to be the output? Sum and carry. So when the inputs are 0, 0, sum is 0, carry is also 0. When there is a high input, then your sum is 1 your carry is 0. And similarly for the third case, the sum is 1, carry is 0. Then for the last case, the sum is 0 and the carry is 1. Okay. Now, we need to get the equation for the output variables yes and carry. So for that, we just consider the output column and we just observe which are all the values are 1 and which input combination is giving a value of 1. Okay. So say for example, if you take this input combination, the variable A has a value of 0 that can be represented as A bar. And the value of B is 1 that can be represented as such. So B, and it is written in the form of a product. So this is the first term which gives an output of 1 followed by the next combination. So when you go to the next combination, the value of A is 1 where it is A and the value of B is 0 where it can be written as B bar. So this is the equation that we obtained for sum. So on looking this, we are very clear that this is A bar B plus A B bar, which represents the function of an XOR gate. So this can be rewritten as A XOR B. Now, let us go to the carry and let us just see which input combination gives a value of 1. So it is the last combination which gives an output value of 1 under the column of carry. So if you take the input combination, the value of A is 1. So thereby the variable is written as such. And similarly, the value of B is 1 and it is written as such. So AB. So A dot B is the equation that we obtained for carry. On looking this, you can make out that an AND gate is sufficient to realize the carry. So now these are the two equations that are related with this half adder. So let us take one XOR gate and one AND gate which is sufficient for realizing the half adder. So let us take an XOR gate. So coming to the XOR gate, the IC number of XOR gate is 7486. When we provide the input A and B, the output is sum. And similarly, take an AND gate where the IC number of AND gate is 7408. The same input A and B is provided so that gives a value of carry. Okay. So now if you just recall the steps whichever we have seen in the beginning. So the very first thing is that we have understood that we need to design a digital circuit in order to perform the binary addition of 2 bits. So we have assigned the 2 input variables and the necessary output variables for the given problem statement. Then we have taken the possible input combinations. Then we have just obtained the output combinations for those. Then we have derived the Boolean expression for the output variables. Based upon the output variable equations, we have obtained the digital logic circuit. So next, let us see how to design a logic circuit for performing the 3-bit binary addition. So coming to 3-bit binary addition, so we need to take 3 input variables A, B and C, in which case if the number of input variable is 3, the possible combinations is 2 power n, where it is 8 possible combinations. So the input variable is A, B, C starting from 000. So the possible input variable combinations are 0, 0, 0, 0, 0, 1. So how can we take this consecutive combinations? So first you initialize with the triple zeros, followed by, as you all know the rules of binary addition, add 1 to the previous state so that you will be able to get the next number. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So now the output variable is sum and carry. So when you have 3 zeros, the sum is 0, carry is also 0. Whenever you have a single one, the sum is 1 and carry is 0. Similarly, whenever you have a single one, the sum is 1 and carry is 0. Whenever you have two ones, the sum is 0, carry is 1. Whenever you have a single one, the sum is 1, carry is 0. Whenever you have two ones, the sum is 0, carry is 1. Whenever you have two ones, the sum is 0, carry is 1. And whenever you have three ones, both the sum and carry are 1. So now, if you look at, let us just take the output column sum and carry in order to derive the equation for designing the logic circuit. So if you take the column of sum, so we have the ones for these four combinations. So now let us write the equation. So sum is equal to, the first combination is, since the value of A is 0, it is A bar, B bar, C. Plus, coming to this, the value of A is 0. So it can be written as A bar, value of B is 1. So write it as B. And the value of C is 0. Write it as C bar. Plus, for this combination, it is A, B bar, C bar. So it is A, B bar, C bar, plus for the last combination, the term is A, B, C. See, this way of representing the variable in the form of a product and making a summation is called as SOP. Sum of the products, where each and every term is called as a min term. So now let us see whether is there any possibility for us to take any common variables out so that we can just form a reduce the expression. Because we would like to reduce the expression in order to reduce the number of gates required for implementation and thereby the cost that is required for the digital design. It is required because to have a compact design and also with less cost. So now, out of the first two terms, if you look at, A bar is common, which can be taken out so that we get it as B bar C plus B C bar. From the third term and fourth term, it is A which is common, so that we can take A common. So we get it like B bar C bar plus BC. If you look at this, this represents the function of an XOR gate. So it can be rewritten as B XOR C plus A into, this represents the function of an XNOR gate, which can be written as B XOR C the whole bar. So now, if X is equal to B XOR C, then we can rewrite it as A bar into X plus A X bar, which is again an XOR function, so that it can be rewritten as A XOR X. And now we can replace the X by means of this B XOR C. So it can be rewritten as A XOR B XOR C. So now this is the reduced expression for sum. So the reduced expression for the sum is A XOR B XOR C. Same way, we can derive the equation for carry. So here, if you look for carry, these are the combinations that gives a value of 1 in the column of carry. So if you look at the combinations, so for carry, this is A bar BC, A bar BC plus this is A B bar C plus this is A B C bar plus A B C. So these are the 4 terms that we get for carry. Again, as we have carried out the reduction in case of the sum expression, let us just see whether is there any possibility for us to proceed with the carry reduction. So here, out of the first 2 terms, we can take C common. So we get it as C into A XOR B plus A B bar plus we can take A common so that we get AB is common so that we can take AB common and we get C bar plus C. So again, this A bar B plus A B bar is an XOR function which can be written as A XOR B, and we know that C bar plus C is equal to 1. So that could be written as plus AB. So this is the expression of carry. So expression of carry is C into A XOR B plus AB. So now if we need to draw the diagram, digital diagram for this full adder, we require 2 XOR gates, 2 AND gates, and 1 OR gate. So I hope you understood how we have framed the truth table for various combinations of 3-bit binary addition and how we have just obtained the expression for sum and carry. So next let us see how to draw the expression. So for which, let me draw the diagram here. For full adder diagram, so the 3-bit binary addition can be carried out by the full adder, which performs the 3-bit binary addition. So let us take input A and B and provide it to an XOR gate, where the XOR gate is 7486. Then take the input of C and A XOR B along with the C, again provided to an XOR gate. So the output whichever is obtained is the sum. Now to realize carry, take A XOR B and C and provide it to an AND gate. So this is A XOR B and this is C. So C into A XOR B. Then take the inputs of A, take the input of B and provide it to an AND gate. So this is B and this is A, so that we get AB. Now as per the AND expression, we have formed this C into AX or B and AB, and now you need to add them up. That is, you need to provide the output of these two AND gates to an OR gate. So provided to an OR gate, so this gives you the carry. So the IC number of AND gate is 7408 and the IC number of OR gate is 7432. So this is the logic diagram which will be helpful for us for executing the 3-bit binary addition. So I hope you might have understood the idea about the binary addition, that is both half adder and full adder. So next, let us move on to multiplexer. So far we have just discussed about what is the general procedure that we are supposed to follow in case of a combinational logic circuit. And as a sample, we have seen the adder circuits in which we have just seen the digital design for half adder and full adder, where half adder is the binary addition, that is performing the 2-bit binary addition, and where full adder is performing a 3-bit binary addition. And before moving on to the multiplexer, so it is also necessary for us to know what will be the output, or if you see it in a simulation window, so what will be the output or the timing diagram that we obtain for half adder and full adder. So coming to the half adder, we just take A. So we take, there are 4 states. So the time period that is taken is 4 milliseconds. Say for example, if 1 millisecond is required for realizing each of the state, then 2 millisecond, 3 millisecond, and 4 millisecond are the 4 states that is required. So now let us take input A. So we know until 2 millisecond, A is 0, 0, after which it is 2. So for your clarity, let me reconstruct the truth table based upon which we decide the timing diagram. So AB, sum and carry. So 0, 0, 0, 1, 1, 0, 1, 1. So 0, 0, 1, 0, 1, 0, 0, 1. So here if you look at, totally four states are there. If one state exists for 1 millisecond, the total time period required for realizing all the 4 combinations will be 4 milliseconds. So that is why along the time axis, I have taken 4 milliseconds. Now, coming to the input column, how are we supposed to set the digital clock? Along A, if you look at, A is remaining in the off state for the first 2 milliseconds, and it is remaining in the on state for the next 2 milliseconds. So whenever the input A is 0, we mean to say that it is in the off state. And whenever it is in 1, we mean to say that it is in the on state. So first let us just project this. So I'm just projecting along the time axis. So A is 0, 0 for first 2 millisecond, 1, 1 for the next 2 millisecond. So here the on time is 2 millisecond. Off time is also 2 millisecond for input A. Coming to B, it changes its state from 0 to 1 and 1 to 0, then from 0 to 1. So for every 1 millisecond, it is changing its state from 0 to 1 and so on. So on time is also 1 millisecond. Off time is also 1 millisecond. So for B, it is 0, 1, followed by 0 and 1. So 0, 1, 0, 1. Now, coming to the sum, whenever A and B are 0, your sum is 0. Whenever your input A and B are 0, 1, your sum is 1. Whenever it is 1, 0, still the sum is 1. And whenever it is 1, 1, the sum is 0. So here if you look at, your sum is 0, 1, 1, 0. So I hope we get the same. So 0, 1, 1, 0. Finally, for carry, whenever the inputs are 0, no carry. Similarly, here, whenever the input is a single one, we don't get a carry. Whenever both the inputs are 1, we get a carry. So the carry is 0, 0, 0, 1. So this is called as timing diagram, or the output that we obtain when we give the clock pulse. So similarly, we can construct the diagram for full adder. So for your reference, I again reconstruct the truth table. So A, B, C, sum and carry. So A, B, C, sum, carry. So 0, 0, 0, both are 0. 0, 0, 1, sum is 1, carry is 0. 0, 1, 0, sum is 1, carry is 0. 0, 1, 1, sum is 0, carry is 1. 1, 0, 0, sum is 1, carry is 0. 1, 0, 1, sum is 0, carry is 1. Then for 1, 1, 0, sum is 0, carry is 1. For 1, 1, both are 1. So when we draw the diagram, it is needed for us to draw for 8 milliseconds, as we have 8 states. So 1, 2, 3, 4, 5 milli, 6, 7, and 8. So let us project it. In order to draw the timing diagram for 4 millisecond, for my 5 millisecond, for 6 millisecond, for 7 millisecond, and 8. Now, for A, if you look at, A is 0 for the first 4 millisecond, and it is 1 for the next 4 millisecond. So when you take input A, until 4 millisecond, it is 0. So 0, 0, 0, 0. For the remaining 4 millisecond, it is 1. Coming to B, it is 0, 0 for first 2 millisecond, 1, 1 for next 2, again 0, 0 for first 2, and then, so B is having on and off timing as 2 millisecond, whereas your A is having on and off timing as 4 millisecond. So 0, 0, 1, 1, 0, 0, 1, 1. Coming to C, it changes its state after every 1 millisecond. So 0, 1, 0, 1, 0, 1, 0, 1. And coming to sum, the value is 0, 1, 1, 0, 1, 0, 0, 1. Then coming to carry, it is for the first 3 milliseconds, it is 0, then it is 1, then it is 0, then it is 1, then it is 1. So this is the output that we will observe upon the digital system design, which is carried for full adder. So I hope you might have understood very clearly how to design a 2-bit binary adder and 3-bit binary adder, and what kind of output do we get in the output window. So next, let us have a discussion regarding the multiplexer. Multiplexer, generally called as MUX, or it is also called as a data selector. It can also be called as data selector. Okay. So generally, the configuration is, it is multiple input, single output, many input, single output. So the general configuration is 2 power n is to 1, where 2 power n stands for number of inputs and 1 stands for number of output, and this n stands for number of select lines. So say for example, it can be a 2:1 mux, or 4:1 mux, or 8:1 mux, or 16:1 mux, where the number of select line for this is 1. So the number of select line for this is 2. The number of select line for this is 3. And the number of select lines will be for 4. So now, just as a moderate, let us take the configuration of 4:1 to demonstrate the working of multiplexer. So when you take, let us take a 4x1 mux, in which we might be having 4 data: D0, D1, D2, and D3, and input such as the select lines S0 and S1, and let the output be F. Say for example, if we want to transmit the data, let us take a case that I need to transmit your data, that is your degree BTech and your discipline EEE. Then let the data D0 be associated with your degree BTech. Let D1 be the data of your department. Let the D2 be the data about your name, and D3 be your register number. So now, which data should I send now? Because though we have 4 input data, there is only 1 output channel to display that. So which input data should now be showcased, and the output will be decided by the select lines S0 and S1. So for which we need to form a truth table. So taking the truth table, let us take the select lines S0, S1, and the output F. Whenever the select line, since the select line was 2, the possible combinations are 0, 0, 0, 1, 1, 0, 1, 1. So whenever the combination is 0, 0, D0 should be shown at the output. Whenever the combination is 0, 1, the data D1 should be shown at the output. Whenever the combination is 1, 0, the data D2 should be shown at the output. Then whenever the combination is 1, 1, the data D3 should be shown at the output. Okay. So now let us get the equation for this F, where it is, since the value of S0 is 0 and S1 is 0 for selecting D0, let us rewrite it as S0 bar into S1 bar into D0 plus S0 bar into S1 into D1 plus S0 into S1 bar into D2 plus S0 S1 into D3. So this is the expression for the output F in the multiplexer. So now what did we do actually? Multiplexer is that which selects the data which need to be sent to the output channel. So it can be of configuration 2 power n is to 1, where n stands for the number of select lines, 2 power n stands for the number of input channels, and 1 stands for the number of output. So depending upon the configuration, we can frame the truth table and we can get the expression for the output. So now let us implement this in the form of a logic diagram. So here we have 4 terms. It means that 4 AND gates are required for executing this. So let us take S0. And since we need S0 bar, introduce it to an NOT gate and let this be S0 bar. Then S1 and introduce it to a NOT gate and let this be S1 bar. And now let us take 4 AND gates and let the input for the first one be D0, for the second one be D1, third one be D2, fourth one be D3. Now, as per this, S0 bar and S1 bar need to be connected. So it means that from S0 bar, then from S1 bar. For second one, S0 bar and S1. For third one, S0 and S1 bar. For fourth one, it is S0 and S1. Just a minute. Then this should be connected as S1. Then the output of all these 4 AND gates need to be connected to an OR gate. So which is the output F. Okay. So now this is the logic diagram for executing the multiplexer. So now let us check for one condition. In random, let us take for D2. So for D2, the value taken is S0 is equal to 1 and S1 is equal to 0. So look at over here. If S0 is 1, what about S0 bar? It is 0. So you know very clearly in an AND gate, if at least a single 0 exists, then obviously the output becomes 0. In the second one, it is S0 bar. So here again it becomes 0, due to which the output becomes the second gate is also deactivated. Coming to the third gate, it is S0 whose value is 1 and S1 is 0. Here it is S1 bar which is 1. So both the values of S0 and S1 is 1. So it is this AND gate which is activated. So thereby D2 reaches the output. Coming to the last gate, S0 value is 1, whereas S1 value is 0. So since we have a single 0, obviously the last AND gate is also deactivated. So out of all the 4 AND gates, it is only the third AND gate which gets activated, due to which the second data D2, the third data D2 is given in the output channel here. So likewise, you can check it out for any of the conditions. So this is how the multiplexer is executed. So this is very much helpful in the data transmission, like extracting the data, both in transmission as well as in the receiving. So multiplexer and the reverse process demultiplexer are very, very essential for communicating the data. So I hope I have just given you sufficient idea regarding the combinational logic circuit in general and the way to execute the half adder and full adder circuits, and also the operation of the multiplexer. So this multiplexer is used in the transmission networks for transmission of the digital packets. So if it is required for you to extend the design for an 8x1, then obviously you need to think about it should be 2 power 3 because the number of inputs, if the number of inputs need to be 8:1, then it is 2 power 3:1, where this is the number of inputs. Then it is 3. So it is the number of inputs 3. Three is the number, then this can be extended such that the number of select lines is 3. So this can be extended, in which case the data can be D0 till D7 and so on. Thank you.